All right, so welcome, students. So glad to have you here. You submitted some really interesting research topics for this meeting, and we're excited to hear about that work in this session. We have a order of presentation that I think was communicated to you that starts with Heather Johnston. Heather is joining us from the University of Michigan, and so the students will have very brief presentations of their work here during this session, and then we'll have some time for Q&A amongst all of them as well. And I'll note that we do have a second session tomorrow at 1 p.m. Central for the second half of this group. So in the interest of time, I'll turn it over to Heather at this point to tell us about your work. Thanks for being here.
Thank you. It's great to be here. The research I'm working on with a few of my colleagues is about public opinions on COVID-19 vaccines, and in particular, using tools from the field of machine learning to make sense of social media data. I think folks are probably very aware, maybe more aware than we wish we were, about how important individual behavior is and individual decision-making is when it comes to public health outcomes. And this is really true in the case of infectious disease, where one person deciding to wash their hands or to practice social distancing, or as we're talking about here, to get vaccinated, can have really important impacts. So I just say that to kind of frame why we're interested in public opinion and why public behavior is kind of what we're trying to eventually get at. So traditionally, public opinion has been studied by surveys, which are good, but they can be quite costly. And both costly in terms of money, but also in terms of time. So it can be really difficult to monitor a quickly evolving situation like a pandemic, for example. So this was true before the pandemic, but it's increasingly true now that public health researchers have been turning toward social media data. Great things about social media data: there's a ton of it, generally freely available, especially on a site like Twitter, where almost everything is public. Downsides of social media data: they're really big, really noisy, and complex. So both complex in the sense that they're in the form of human language, which our conventional statistical methods don't handle very well. But they're also short text, typically. Twitter has the signature sort of character limit, and they're also very casual. They have slang and emojis and other things that traditional natural language processing doesn't always handle very well. So we turn to some tools from machine learning, and the task that we're trying to do here, to be more specific about the task, is we're trying to classify tweets into categories. So we're identifying themes of tweets, classifying each tweet into a category, and then so far what we've done, but this is still a work in progress, is visualizing subtopics within categories and tracking changes in the conversation as measured by what themes are appearing throughout the time period of interest. So now to get into the actual data and methodology, we started with 6,000 tweets identified as being about COVID-19 vaccines. Some really wonderful researchers have started gathering or have been gathering tweets specifically about COVID-19 vaccines. So we start with just the sample of 6,000 of them. My colleague Madeline Powers, who is a public health student, iteratively read through tweets, classified them, then defined different topics and sort of refined. What I'm trying to say is, like, she really refined these topics iteratively, defined the topics, read more tweets, refine the topics. And we eventually settled on these 7 topics, which we classified the 6,000 tweets by hand into. So then we get to the actual classification model, and we're using a BERT model, or bidirectional encoder representations from transformers. We used two specific BERT models, which were pre-trained on Twitter data, which was collected after the start of the pandemic. So these models had seen words like coronavirus and COVID, and even like some talk of vaccines. We then fine-tuned these two BERT models on the context-specific classification task. So our human identified 7 categories. And then we applied the model to a larger sample of nearly 1 million tweets, a little over 800,000. And these were English language tweets sampled from January to August of this year. And they were all about COVID-19 vaccines and people's opinions. And so we used our model to classify the topics. And what we get is really good performance, despite our small, relatively small training set. The test set performance is excellent. We get nearly 80% accuracy. And then looking at word frequency, we see that that the words we see in these different categories are consistent with what we who hand labeled the tweets would expect, which is good. That indicates our model is performing well. And then we're working on a few different use cases for this model, but one of them will be what we see in the bottom right here, which is tracking the change in conversation over time. So we start to see trends in the different topics that have been discussed. Yes, thank you all. That'll a little over my 5 minutes, so I'll stop there.
No worries. Thank you very much. Very timely and interesting research. Thanks for sharing that with us today. Audience, feel free to put questions in the chat at any point for the presenters, but we will have time at the end to ask them directly as well. But we do have several folks to present today, so I want to move quickly along to our next presenter, Sushanth from University of Illinois.
Hi, my name is Sushanth, and I'm a graduate student at the University of Illinois, Urbana-Champaign. So I'll be speaking about my research on the Bangalore vaccination drive and the insights I could gather. Right in the midst of the second wave, which was devastating in India, the government finally announced vaccination for all. But given the huge shortage of vaccines, the number of people who are trying to get a vaccine was very high, and not many people were successful in trying to book a slot. Given this problem, developers in Bangalore started creating bots in Twitter and Telegram that gave out alerts to people as soon as vaccine slots opened up in hospitals. While there were a lot of people getting these alerts, only a few of them were still successfully able to book a slot. But the mass panic made people invest a lot of time into this, and a lot of effort was going on, and people spending time into this. So I thought of this, and I came out with an idea of collecting all the data that the Twitter handle were pushing out with all their alerts. So I created a dashboard that would give like what particular time a particular hospital would open up their slot, and usually. So I'll just open up my dashboard. So over here in the dashboard, people could easily see that Apollo Hospital, for example, had the highest number of slots. And when you look at the distribution, you can see that people were mostly successful in booking a slot if they invested their time during 7 p.m. or say 10 p.m. And if people were particularly interested in a particular hospital, they could just put a filter in the hospital. Let's say you want to look at Apollo Credit, and you could see that most of the slots were opening up during 7 p.m. So people could invest their time during the 7 p.m. Timeline. And over here, if you see at Apollo Jayanagar, most of their slots were opening up during 7 a.m. So this saved a lot of effort for the people. And at that point of time, I had 14,000 active users widely using this tool that I created. Yep. So this was all for my presentation. Thank you so much.
Thank you very much. Very interesting. Again, very timely as well. I would encourage both of you, Heather and Sushanth, to have a look at our COVID Information Commons community as well. We may be able to have you present to that audience. This work is very relevant to that community. We're going to move next to Jongwon Park, also from University of Illinois.
Yeah, hello everybody. I'm a student at University of Illinois, and today I'm here to present my research on Continual BERT. So what is Continual BERT? So in the last 2 years of the pandemic, there has been a drowning influx of COVID-19 papers. One of the science.org articles states that there has been more than 23,000 COVID articles from just January to May of 2020, which is more than 150 articles per day. So the problem is that all the researchers and even the audience can't comprehend and understand all those papers while there's new ones coming up every day. So the research question here was, how can we transform the massive influx of COVID-19 literature into concise feeds for researchers and readers to understand in simple words? And the solution that I came up with is called Continual BERT. It uses a bidirectional transformer, which is a NLP, natural language processing model for machine learning. So there are three components to it. First, it continually learns from chronological feed of scientific literature, and it adaptively recognizes critical sentences and combines them into a concise summary. And it is trained on a medical literature data set, including those related to COVID-19, to deal specifically with the rapid influx of scientific literature during the pandemic. And on the right is a very brief summary of what part of the model looks like. And I'll go to the next slide. It uses what's called the elastic rate consolidation. I'll just go very fast through this, but it basically tries to, in clusters of data, it basically tries to learn the best parameters as possible while not forgetting about the previous task that it has learned. So by using EWC, which is a main framework used in many of the continual learning setting, it tries to learn from the past data, and then while learning the new data, also tries to retain the information from the past data, which is different from many machine learning algorithms in that it tries to create what's called memory in machine learning. Yeah, so Continual BERT mainly trains on the scientific literature and articles with high quality summaries. So some of the high quality summaries include well-written abstracts, concise summaries provided during peer reviews, and manually written summaries by readers or some other institutions that try to write them. And we assume that there are well-grouped clusters of literature and articles, meaning that we assume that they are categorized into certain features so that we can divide them into multiple training steps. And the data are basically grouped into clusters of certain categories, and the models trained on a cluster after cluster, trying to memorize on the previous data while also trying to learn from the current data to produce the best summary as possible. And also some articles are used to test the model. And as this whole model is for, the model is tested on the new influx of data, of literature coming in every day. Yeah, so the current data sets the model was trained and tested on there are three data sets. One of them is CTD Pfizer. It's 88,000 scientific articles and text. The other one is one by Stanford. It's called SciSumNet. It's 1,000 papers with high quality summaries. And the other one is Core 19, as many of might have heard of. It's basically an aggregation of all PubMed, Central, and other journals articles that are aggregated without much human annotations. So this machine learning model was trained on about 600,000 scientific literature and articles. Yeah, so this is one of the example data that the machine was trained on. So on the left is the original abstract provided by the authors, and on the right is a manual summaries and research highlights provided by another article. And going on that example result, the evaluations from the model shows that while the left one is more of advanced languages, the right, the evaluations made by the Continual BERT tries to make it into simpler terms so that everyone can understand it. And it also tries to truncate the summaries or the abstracts, the whole papers, into less than 10 sentences so that it can, so that readers can swiftly go through literatures at the time. Yeah, so again, this is a very data-centric model. All the guesses on the literatures, all the summaries produced by the models are based on past data, and it extracts crucial parameters from the previous data, so it reflects a lot of the biases and variances in data clusters. So it is crucial to have good data feed into the model. And again, we have many assumptions about the data. So it is really important that there are good data that are going in, especially the summaries. Yeah, so that's it. Thank you.
All right, thanks very much for that. I think, so far we've seen 3 examples of COVID-related data that are all very different from each other, but the sort of unifying theme is that there's too much data for humans to comprehend, and we need these tools to analyze them. So that's all very interesting approaches that you have taken there. Next up, we have a student from Iowa State University. This is Yicheng.
Yeah, okay. Hello, everyone. Hello, everyone. My name is Yicheng, and my research topic is general purpose open source program for ultra incomplete data oriented parallel fractional hot deck in imputation, which is denoted as the UP-FHDI program. So the incomplete data program is very common in brute science. So here we have shown two sample incomplete data sets from the infrastructure and engineering domain. And from this two data sets here, we can see a lot of missing values here, marked by the NA values, and how we can reliably fill in the missing values in these two example data is a very serious problem. So in machine learning community, there exist two widely used method to fill in the missing values. One is called the naive imputation, which just simply use each variable's mean to fill up the missing values. The other method is just the removal of the entire unit, which has the missing values. However, both of these two methods have some statistical problems. So for the removal of the entire unit may lead to the loss of substantial information, and the naive imputation method may introduce unexpected bias and may lead to low accuracy in machine learning or in the static predictions. And the naive imputation may also lead to the incorrect statistical inference. So the other popular imputation method to fill up the missing values can be the multiple imputation, which create M-completed datasets for the full imputation uncertainty. However, multiple imputation is going to be quite difficult to use in practice for the general researchers, because multiple imputation requires two preconditions. If these preconditions are not met, the MI variance estimator may be inconsistent or considerably biased. So here we recap the main challenges of existing imputation method for the big incomplete data. So firstly, most of the popular imputation methods requires the distributional assumptions, which are very difficult to set up for the general researchers. And secondly, the computational limitation may prevent this popular imputation method to apply for the big incomplete data in the brute science. Therefore, our choice to handle the big data in imputation is to choose the fractional hot deck in imputation. So our research group has already developed and shared a public open source R package FHDI. Here I summarize the strengths of our package, but still this R package FHDI is not suitable for tackling the big incomplete data. And here we summarize the motivations why our research group need to further develop the UP-FHDI program, where the key motivation is that the limitations of the Siri R package FHDI regarding its regarding extremely long running time and the huge memory requirement. This is a key motivation why we need to develop our new program. So our research group classified the big incomplete data into three groups. The first group is called big N data, where the number of rows is much larger than the number of columns. And the second group is called big P data, which is also called the high dimensional data, such that the number of rows is less than or equal to the number of columns. So our first version of the PFHDI is handles these two groups of big incomplete data very, very well. However, the PFHDI is still not able to handle we call it ultra data. So where the number of rows and number of columns are both extremely large. So based on this purpose, our research group developed the UP-FHDI program, particularly important to the ultra data where the N and P are both extremely large. So we summarize the key procedures of the UP-FHDI, which include the parallel cell construction, parallel cell probability estimation, parallel imputation, and parallel variance estimation, including the jackknife variance estimation and the linearized variance estimation. So the library we used in our UP-FHDI program to perform the parallel computing is MPI. And the high performance computing facilities we used to develop and test our program is Condo 2017 and the TACC's the Stampede2 platform. and I would like to show how the UP-FHDI program processes the big data via the parallel file system shown here. So for all of the processors, they're going to communicate with each other via the communication channel. And we store the input data and temporary data all in the local storage provided by the high performance computing for facilities. And all of the sleep processors, they only fetch the required data to their own memory. And we adopt this optimum overload I/O protection system to adjust extensive I/O workload here. So we provide the different type of example big incomplete data for people to test our program UP-FHDI. Here we have the following example is a big N or big P big incomplete data sets. We have posted this data set to the IEEE data port. And we also provide 7 real-world ultra data sets which is also available in the IEEE data port for users to test our program. And finally, I would like to summarize the strengths of the UP-FHDI. And remarkably, so our program can cure incomplete synthetic data with 1 million instances and 10,000 variables of 80 gigabytes with 30% missing rate only in 35 hours with in total 240 per processors. So this is just show how powerful our program is. Yeah, so this is a reference I used in my presentation, and thank you very much. Thank you.
Thank you. Yeah, thank you very much as well. We're going to move next to Samantha from the University of Illinois.
Hi, Hi, thank you. Thank you for having me. Right. So I want to introduce the idea of describing a scientific workflow, and I'm also going to talk through a specific use case to kind of demonstrate my approach with this. So really quickly, a little bit about me. My name is Sam Walkow. I'm an informatics PhD student at the University of Illinois, and I focus on understanding data visualization analysis tools and working in the open source development world. So my work is in supporting open source development and also how to make open source more sustainable. And what that means is, how do we get more people involved, and how do we keep people who are involved in it for the long term? And one of the things we've been identifying in this work is barriers to computational work and barriers to open source work, working on understanding them and understanding how we can lower those barriers to get more people involved and get these code bases to be a little more robust. To better understand this, we're using a use case in YT. YT is an open source Python package used for volumetric data analysis and visualization. And it's developed particularly for computational astrophysics. And what we want to understand is the cognitive load involved in using a tool like this and other tools like YT. And what we run into is something I like to call the learning cliff. And the learning cliff is really about a researcher and their output and all the work that goes in between that. And the base level is your domain knowledge. You use your domain knowledge to reason with the data you have to create something meaningful in terms of output and analysis. And in computational work, it's quite a bit more complicated than that. You typically need to know a programming language like Python. You need to work with an environment like Jupyter. You need to know a version control system like Git, a notoriously fun one to work with. You need to know domain-specific libraries like YT to help you plot, visualize, and analyze your data. You also need to work with specific types of data, different file formats, different file structures, and everything that comes along with that. And this is really the minimum of what you need. If you work in computational work, there's a lot more to it than this. There's also a lot more domain-specific libraries you might need to use as well. YT is just one of them. And all of this is part of your cognitive load that you have to work with. So my work involves working with libraries like YT and in Python to see if we can smooth the cognitive load and kind of reduce it. So what does this work look like? It looks like working with YT and other libraries like YT to identify common methods and functions. So what actions is the code taking and how is it doing this? It also looks like harmonizing these tools to understand not just the overlap in functionality, but overlap in user workflows. Where is the overlap in how users think about and reason with these tools? And the idea here is to create an interface to visualize and analyze natural science data that does not require Python or YT or knowledge of those things to use it. And we call this the analysis schema. And it's a way to describe your workflow in sort of a configuration file where you can find keywords and add values to them and have the code run. And you don't need to know a specific programming language or a specific domain library. And in this way, you don't have to wrestle with your domain knowledge and then also with the cognitive load of so many different tools. So what kind of data goes into a project like this? Data comes in the form of open source code bases, the methods, functions, classes, type annotations, and also the ways of thinking encoded with them. How does the code reason with the data it gets? Also data from users, researchers, and open source communities, people who use and develop these tools all the time. We want to know how they work with domain knowledge. How do they work with the cognitive load? What data are they trying to use? And finally, we want to know about the data on how people are using the analysis schema, navigation, accessibility. Is this in fact reducing cognitive load, making it easier for researchers to just use their domain knowledge to work with the data? So some future directions we'd like to take, we'd like to have a way to add context to data analysis because we're abstracting away a lot of the methods and functions. It'd be nice to have a way to specify context. And that would look like data from ontologies, the human data we're going to collect from open source communities as a way to manage that and make sure we're not abstracting away too much. And we look at this as a way to translate between users, developers, and communities, a way to get more people involved, and hopefully they'll become developers, but also a way to make a very specific program like YT, something that's just for astrophysicists, more usable across domains. So people in, say, medical imaging and other natural science domains might also use this type of code and do these type of visualizations, but previously had trouble accessing or learning YT or learning Python. And those were barriers that just need to be there. So thank you for having me, and thank you to my advisor, Dr. Matthew Turk, and my collaborator, Dr. Chris Havlin.
Great, thank you, Sam, so much. We'll follow up with some questions about that in the Q&A session. We have two more presenters. Emmanuel is first, and then Pavan will finish off for us.
All right, so my name is Emmanuel, and I'm a PhD student from civil engineering here in University of Nebraska, Lincoln. So today I'm just going to be I'm going to be presenting on a single value decomposition based novelty index that we developed for damage detection in bridges. So currently, my research team is working on a project that's supported by NSF. And our goal is to develop technologies and tools that can be used to identify and assess damages in bridge. So in order to do this, we performed some full-scale field experiments on a concrete bridge mock-up and also on 2 in-situ steel bridges that are due for replacement in some rural areas. And then during this field experiment, our goal was to collect as much data in terms of the measured response of the bridge, specifically the strain and the acceleration. And then after the whole test, we utilized singular value decomposition to this data, and then we used the result as an input for our novelty damage framework. So this shows the instrumentation plan for one of our field scale experiments. So this shows the instrumentation plan for the sensors. We had a number of string transducers from BDH, which was placed on the bridge. And yeah, I'm just going to be explaining briefly the process of how we collect this data. So we have these string transducers installed on the bridge. Here you can see 2 sensors installed on one of the beams, and then these string transducers are connected. So 4 numbers of these string transducers are connected to a data acquisition nodes. And after this, we set up a base station. So this base station is like the mid communication hub, the central communication hub between the STD nodes and also between the STV Live application on the computer. So once this is set up, then we can start recording our data from the bridge, and when our data on the bridge due to movement of vehicles on the bridge. So one of the interesting thing about this work is that in this field test is that we induce 3 damage scenarios in this field test. So in the bridge mockup, we have 3 damage scenarios. We had the concrete and the concrete barrier and the deck being cut. And for the steel bridges, we also have two damage scenarios where we had a cut on the web and also on the flange. So after this, for each of the damage cases, we had a number of vehicle passages on the bridge. And after this, the data was collected, and then we filtered and processed. And then we stored this in a snapshot matrix in MATLAB. And then we applied singular value decomposition, which is like a statistical tool to detect damage. And then the proper orthogonal modes, which is pumps that is derived from the SVD of this snapshot matrix, is used as an input for the novelty detection framework. Here, this shows the result for, this shows one of our results. So for the bridge mockup, this shows the novelty index, and you can see from here that at each stage, from the undamaged state of the bridge to each damage scenario, the novelty index increases. So we validated this tool, which is the SVD novelty index, with data from the other 2 steel bridges. And here also you can see that the novelty index increases after the undamaged bridge to damage 1, which has to do with the flange cuts, and then down to the second damage. The the result here also shows this also shows the result from the other bridge. And so for me, I can just conclude that we're able to develop a tool, a novelty index tool that can be used to detect damage in bridges from the data we collected during our field test. Thank you for listening. Yeah.
Thank you very much, Emmanuel. We have several of your colleagues speaking on our call tomorrow as well to talk about their bridge-related work. So it sounds like you have a great group out there in Nebraska working on that topic. All right, we're going to switch to Pavan to hear about some business analytics kinds of topics as well.
Thank you so much, John. Thanks for the wonderful opportunity. So today I'm going to talk about one of the personal project. So where I worked with one of the mobile gaming companies. This was a case of South African mobile gaming company, and they have a huge base of customers, and they wanted to see they wanted to identify the customer lifetime value of all their customers to be able to target the customers in a better way using the promotions, so that they can increase the customer retention rate. So the literature on these customer lifetime value models has dated very back, and it has started using survival analysis and customer lifetime value models. So this is basically dominated by buy until you die models, where we mainly consider two factors, where the transaction rate of the consumers that we have, that is determined by the distribution of the revenue, and the second one is the customer churn probability, that is when do the customers switch. So using these two distributions, we typically talk about the buy until you die models, and we use these two factors in modeling the factors. So the main idea here is to answer the key questions. Those are: how many customers are active, and how many customers will be active 1 year from now, and what is the probability that the following customers are going to be churned or shifting the company, and then finally, how valuable is any customer for the company. So this can be determined by the distribution of the revenue and transactions that they're going to make. So as I said, there's a lot of literature going on, but main idea, it dates back to 1960, and then the distribution of both the revenue and the churn has been developed by scientists using different distributions. So I focused on a factor called beta, gamma, and negative binomial distributions, where we use these two distributions to model both the customer revenue and also the churn probabilities of the customers. So here the data that the company provided consists of two data. One is the revenue from each and every player. So the brand ID determines the product that they are targeting, and then the deposit date and deposit amount. And then coming to the demographic side, it talks about the registration and what are the other demographic criteria like age, gender, and country. So these two data are useful in forming the distribution for these two factors. And then this model, what I'm talking about is basically beta, gamma, and non-negative binomial distribution. Here we assume that both these processes, the process of the transactions made by customer is Poisson distributed with a rate of lambda, and then the transaction rate follows the gamma distribution, and similarly the customer churn rate follows a beta distribution with a churn probability of p that we are going to model. And you can see that I have done this analysis using the RFM analysis, which is basically the topmost used analysis in the marketing domain, recency, frequency, and monetary value domain. It talks about how recent the transactions between customers are, and what are the how frequent the transactions are, and the expected sales value. Using these two, using these three factors, we'll calculate the probability of the customer being active in the next couple of months or the time period that we are focusing on. And then we can finally calculate the predicted customer lifetime value using these two factors. So this is basically the work that I focused on using that paper by Fader and Lee. This is the buy until you die models. But then it has some issues with that is coming with it. One is that it suffers from algorithmic complexity, because with the increase in customers, the big O increases very heavily as you go to companies, very big gaming companies. And also it assumes independence between the transaction process and also the churn process, which is sometimes not very correct. And there are several other techniques that are being developed. Some of them are Monte Carlo and Markov chain, and also the Pareto methods, which kind of consider the covariance between these two distributions. And then these are limited. These are the parametric assumptions, which are sometimes limited to the parameters that we are going to assume in developing these models. So this is basically the work that I have done. Thank you so much.
Thank you very much, Pavan. Thanks for joining today. All right, so now we have some time for discussion and questions. If folks have questions, feel free to put those in the chat, or you could also unmute and just ask them live. We have all of our presenters with us. I'll go ahead and start while folks are thinking about questions. I think one of the things that stuck out to me in Sam's presentation was, regardless of what discipline you're in or what kind of research you're doing, there is sort of a plus and minus to the number of tools that are available that have been developed in data science and disciplines as well to manage research data. And so I think you really highlighted some of the challenges of working with research data these days, where you have so many choices for tools and what to use to do analysis. I'm wondering how the presenters are dealing with that in your own disciplines, in your own research. What are some of the ways that you're approaching that challenge in understanding, the range of tools that are available, what's most appropriate for your research problem? I think you all used very different kinds of statistical methods and approaches. So maybe talk through a little bit of how you're dealing with that information overload problem.
Well, I can start. I think I very simply just end up picking one thing. I'm going to learn Python. I'm going to use this tool to do my research. I'm going to use this editor, and I just decide to try and stick to it, kind of for better for worse, even if there's something better out there. And I enjoy learning new things, and I try to engage in that with kind of a playful mindset. It's so to get over some of the fear and imposter syndrome of using these things. But in the end of the day, I just okay, I'm doing this thing. I just have to stick to this track, and go with that.
Great. That's a very pragmatic approach, and I'm sure that you have some context that you use as well, but at the end of the day, you have to choose something to use, and so that's a good strategy. What are other folks doing? Do you have input from your advisors? Do you have fellow students who are recommending tools to you? What's your approach?
For me, I've found a lot of value in collaboration. So I'm fortunate to be working with a great team, and we have a lot of overlapping skills, but also some complementary skills. So where I might do most of my work in R, and I can make a nice ggplot output, someone else might be really good at implementing a machine learning model in Python. Mm-hmm. So I think figuring out who knows what and just being really quick to ask for help and to offer help has also been key for me.
Mm-hmm. That's great. Thank you for that. I feel like there's an opportunity for folks who are in maybe the information science world to assist maybe with classification of software, ways of structuring metadata that allows you to, regardless of what discipline you're in, try to find tools that are appropriate for analyzing a particular kind of data or doing some kind of analysis. So there's a potential opportunity there, I think, for folks. Other questions from the audience at this point that you have about the presenter's work? We had quite a diverse set of projects that you were all presenting. Some of them were very real-world, hands-on things, like the bridge infrastructure project. Emmanuel, can you talk a little about the sensors that you were using? Are those like vibration sensing systems? What kind of tools were you using to collect that data?
All right, thank you. Yeah, so just like I said earlier on, these sensors are contact-based, so we need to connect them to the bridge. And sometimes so that takes us to know the specific areas where we need to put the sensors on the bridge. So before that, we do like we do some simulations with finite element, and then we try to know the best positions to locate these string transducers on the bridge. And after completing that, then we know the appropriate place that we can put the string transducers on the bridge. Then also, this string transducer, they also provide time histories of deformation. So like when we have vehicles going over the bridge and then we're recording, they try to show us the time history of deformation for the period, Yeah.
Very interesting. Yeah, I think one of the directions I'm going here is, how do you know that your data is good? And so, I want to open that up to Heather as well, who talked about, looking at social media data. There's a lot of vaccine information that is put out by reputable, public health organizations, but there's a lot of misinformation and disinformation out there as well. And so I don't know if you can speak to, your process in looking at that set of data, and was there any work that you guys did around looking at accuracy or intent of posters, things like that would help you understand which of your data is useful to people and which is more noise kind of data?
Yeah, so that's something, that kind of misinformation identification is something that we had initially thought was a really interesting direction to take this research. And I still think it would be a really interesting direction, although there are a few other folks I know of working on that at the moment. And what we found that was kind of interesting, and I found this as part of the University of Michigan's Big Data Summer Institute, and we had a whole bunch of students working on this, is one of the things we were trying to do is identify different attitudes toward vaccines based on sentiment. So adapt more existing sentiment analysis models and natural language processing techniques to whether someone was pro or anti-vaccine. And that turned out to be really, really hard because the sentiment of a tweet often doesn't really have much to do with whether someone wants you to get vaccinated or not. So yes, I absolutely think that's a super interesting topic and something that we're looking into collaborating with other folks on, into using sort of marrying our classification model with misinformation identification models, because there's a lot of similarities between them. And also, I think in many ways, misinformation models can be made more robust. This is just my hypothesis, but I think that our method, for example, one of our categories is skepticism. And I think that subsetting to just tweets expressing skepticism will really improve the accuracy of misinformation identification models.
Oh, that's very interesting. Yeah, I mean, I sort of see that across multiple projects here that you guys have presented, whether it's Heather's data set of the tweets or whether it's Sushanth's vaccination data, in both of those cases, there's some reliance upon unknown data producers in terms of what their intent is and things like that. But I can see that also with the publication data that Jongwon is talking about. That all of those papers that were produced around COVID were very early on in our understanding of the virus, right? And so it may turn out that some of what was in those papers was not accurate when we learn more about it, but that's the best available information that we have at the time. And so, accounting for error, accounting for misinformation, active disinformation kinds of activities is probably something that we need to keep in mind when we're looking at data that we're getting from places that we don't necessarily control. Emmanuel controls pretty much what the data is that he's getting from the bridge because he controls the sensors and can account for variation in traffic and things like that. But for data that we're acquiring from other sources, we don't always know, the provenance or the accuracy. And so I think that's something that could be interesting to think about in building some of the models that you guys are talking about. All right, we just have a few minutes left here. Any other questions, comments from folks, panelists, or audience?
So can I just make an additional comment? So even in our side, despite the fact that we have data from a controlled situation, it's also important that we also check the data, because sometimes these instruments that are used, like the strain gauges, they get to give you wrong or bad data. And sometimes we need to go through some process of filtering or trying to detrain this data just to make sure that they are accurate and they are good enough for analysis.
Yeah, absolutely. I think the data cleaning step in data science is one that it can be kind of boring, but it's really important for that validity down the road. So yeah, for sure. All right, well, this has been great to have you guys on the call. I'd encourage you to tune in tomorrow for the second session that we have with other students. But I also encourage you to take a look at our data science student community. I'll put the link in the chat here. We have a monthly webinar that presents the work of a particular data science student group. We are trying to get that onto a more monthly schedule. We had a call this week with a group that does consulting with different groups, either academic or industry and government. And so that'll be up on our site soon. So I'd encourage you, if you're part of student groups that are doing data science activities, feel free to reach out to us and we'd be happy to have you participate in that webinar series. But we are trying to build that student community out so that folks have a way to look outside your institution, outside your department, at folks who are doing similar work in the region, similar kinds of use of tools to help build your network and build the community that you can engage with. So I'm happy to have you join that if you're interested. But thanks again to everybody for joining. It was really informative to hear about the work that you're doing.
Thank you. Thank you so much.
Thank you.
Thanks, everyone.
Thank you.